S. Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
Ever wondered that why benzene, which has 3 olefinic groups, doesn't behave like a trialkene? It has nothing like similar to a trialkene or a molecule which has 3 alkene groups in it. The answer to this will be given in today's video, which will be about aromatic hydrocarbons. Hi everyone, my name is Manika and today I'll be taking the topic on aromatic hydrocarbons. Welcome to our channel on S. Chand Academy. To get more information about this topic, you can read about this in our book by S. Chand Publishing, the link to which is given in the description box below. Let's start with it. Aromatic hydrocarbon, as the name suggests, must be having an aromatic moiety in the organic compound. Hydrocarbons are basically classified into 2 categories, aliphatic and aromatic. Aliphatic are again divided into 3, alkanes, alkenes and alkynes, and depending upon the functional group they have, we have numerous variety of functional compounds in our organic chemistry. Aromatic hydrocarbons must have an aromatic ring in them, and it must satisfy the condition of aromaticity. That is, an aromatic compound must obey the Huckel's rule. It should have double bonds in conjugation and it should be planar. So these are the 3 primary requisite conditions which must be there in an organic compound to be classified as aromatic. So the basic organic compound which comes under the category is benzene. Benzene, the structure was elucidated by Kekulé in early 18th century. The formula is C6H6, and if you look at the structure, it has 3 double bonds placed alternatively between the carbon-carbon atoms. So to a layman it may look like as it has 6 carbon atoms, 6 hydrogen atoms, 3 olefinic groups. So it must undergo all the reactions related to the alkenes like addition reactions, so on and so forth, and it should undergo the dissociation also, all of the olefinic linkages like the alkenes undergo, or you should form the dihalides also, but nothing of this sort happens with the benzene. Why? The answer to this which will come eventually. Benzene has a hybrid structure. It has a resonance structure. Before I come to the resonance, let me give you few evidences to how this structure of the benzene which we have in our chemistry today was discovered. So benzene itself resists any addition reaction, any kind of halogen addition like the alkenes undergo. The reaction it undergoes are the substitution reactions. Also, the heat of hydrogenation of the benzene are not in the coordination with the heat of hydrogenation that we should get for a trialkene. Another important evidence which comes from the benzene is that about the bond lengths. In a molecule like benzene, which has 3 double bonds and 3 single bonds, it should have different bond lengths, right? The C double bond C bond length should be shorter as compared to the CC bond length, but this is not the case. In the benzene, all the bond lengths are found to be equal. All the carbon-carbon bonds are of equal length. So this gives a click to anyone who is studying chemistry so as to what is different with this molecule. The thing is, if you look at the molecule very closely, each carbon atom has an unpaired electron on it. Okay, apart from the sp2 hybridized orbitals which are there on every carbon atom in the benzene, the 6 electrons which are unpaired, all of them undergo delocalization over the benzene ring and they form the pi bond, and this pi bond acts like a cloud. So there is a delocalization of 6 pi electrons over all the 6 carbon atoms in the benzene ring, and this gives rise to hybrid structure between the two resonating structures, giving rise to a hybrid structure which we can call as benzene. as I was discussing, that the evidence which we got from for the hybrid structure of the benzene comes from the heat of hydrogenation. Over here I just forgot to mention it initially, that for benzene the heat of hydrogenation is much less than the value which should be expected. Like for cyclohexene it is around 28.6 kilocals per mole. So for benzene it should be 3 times that value, that is, it should be close to around 86 kilocalories per mole, but it's not the case. For benzene the heat of hydrogenation is just 36 kilocalories per mole, much lower than predicted. So this was quite an important evidence to point us towards the resonating structures of the benzene and thereby giving the hybridized structure. As far as the properties of the benzene are concerned, just as I said, it will give you no reaction with the bromine in the presence of CCl4, no reaction under the KMNO4 conditions, cold KMNO4 conditions, and none of the hydrolysis reactions also. So answers to all these is given by the resonance. So can you just convince yourself with the resonating structure of the benzene? And because once you are clear with the structure of the benzene, the most of the aromatic chemistry becomes crystal clear. Let's look at naming some of the benzene derivatives. The monosubstituted derivatives of the benzene are simply named by their special names. For example, if the benzene is substituted by a CH3 group, it will be named as derivatives of toluene. If you have an OH group, phenols. If you have a carboxylic group, benzoic acid, derivatives of benzoic acid. If you have a CHO group on the benzene ring, benzaldehyde, derivatives of benzaldehyde. If OH and CH3 both of them are there, then the molecule will be cresol, and depending upon the position of the OH group, they will be ortho, para and metacresols, right? And for halogens you can have bromobenzene, chlorobenzene, fluorobenzene. So these are the monosubstituted, quite easy and simple to name. And nitro हो जाएगा तो nitrobenzene. For sulfonic acid, benzene sulfonate. So for with each functional group, the property of the benzene derivatives changes depending upon the functionality which is there on the aromatic ring. And one more important thing which I want to mention over there is that these derivatives of the benzene are interconvertible. You can start from benzene as a precursor and go on to synthesize any derivative of amine or benzoic acid or anything which you want to synthesize, be it in the drugs, be it in the industries or wherever, and in the synthesis of natural compounds also. So when you come to the naming the synthesis or name the dye substituted benzenes, so there are 3 types of dye substituted benzenes: ortho, meta and para. That is 1,2 substituted dye substituted benzene are ortho, 1,3 dye substituted benzene will be meta, and 1,4 dye substituted benzene will be para. That is, the substituent will be named as the para substituent, and the one which is on the first position will be the primary group. Say for example, over here on the screen is ortho dibromobenzene. The second one is metachloronitrobenzene or 3-chloro-1-nitrobenzene. The third one is 4-bromotoluene, right? It's a derivative of toluene, so it's 4-bromotoluene. The tri-substituted benzene usually do not have many isomers like the di-substituted benzene. They are named according to the substituent that are attached and the priority order. Apart from the benzene, there are other sets of the aromatic hydrocarbons in the chemistry. Suppose 2 benzene rings are fused together at 1,2 position, it becomes naphthalene. And then another one is anthracene. These are called polycyclic aromatic hydrocarbons, which have a separate set of the chemistry to discuss with. Here we are focusing just on the benzene and its derivatives. And the third one is phenanthrene. So each of them has different chemistry. So let's start with the synthesis of benzene. Benzene was first isolated by Faraday in 1825 from pyrolysis of whale oil. The next synthesis came by Hofmann, who isolated benzene from the distillation of coal tar in 1845, and coal tar is still a source of benzene. It is one of the distillation fractions of coal tar, or petroleum also is an important source of benzene. The first laboratory synthesis of benzene was done by Berthelot by using acetylene. He passed acetylene over a red hot tube and the product which was isolated was benzene. Other common laboratory methods which I want to mention over here are from decarboxylation of aromatic acids. Say for example benzoic acid, if you heat it with calcium oxide, the product can be benzene. Phenols on reduction with zinc dust can also give benzene. Apart from carboxylic acids themselves, sodium salts of carboxylic acids can also give benzene. This happens by reacting with them with sodium hydroxide and again calcium oxide, and the pyrolysis will give benzene, right? And another important reaction which is doable in the laboratory is opposite of sulfonation reaction. Sulfonation is an important electrophilic aromatic substitution of benzene. So इस reaction का जो reverse होता है that is desulfonation. So sulfonation का reverse is desulfonation, it will give back the benzene. So once you get the sulfonic acid, benzene sulfonic acid by electrophilic aromatic substitution, you carry out the hydrolysis of that product and the one can again retrieve back the benzene, right? So these are the few common methods to synthesize benzene. Benzene is quite an important and versatile reagent in the laboratories. It is immiscible in water, and because of this it is used as a quite a popular non-polar solvent in the laboratories. It is also known to be cancerous, so its use has been widely banned worldwide owing to its toxicity, but still it is being used as a part to make synthesis industrial products like rubbers, tires, dyes, detergents, drugs and so on. So its use is inevitable even though it is toxic. It's a natural part of crude oil, gasoline, etc. also. So let's look at the reactions of the benzene. Benzene undergoes electrophilic aromatic substitution reaction, as we have discussed previously also. That why substitution reaction? Because all the electrons in the benzene, the electrons in a benzene ring are delocalized over 6 carbon atoms. If you look at 2 pi electrons, say for example here between C1 and C2, these 2 electrons are not free to react with any reagent as such. If this molecule will react, it will react as a whole with electrophile or the nucleophiles. It can undergo easy electrophilic substitution reactions. We are not discussing other reactions related to benzene over here. I am just focusing on the electrophilic substitution. So what will be the electrophile and what will be the nucleophile? Obviously benzene, since it's an electron rich molecule, it will be reacting with the electron deficient compound, say electrophile. Now this electrophile which we want to use for such reaction must be electron deficient as much as possible. So to increase the electrophilicity of the electrophiles for electrophilic aromatic substitution reactions, Lewis acids are a requisite condition. So that is like they are mandatory for carrying out electrophilic aromatic substitution. Why? Because benzene is quite a stable molecule. What do you think will make benzene lose its aromaticity or lose its stability and go on and react with some electrophile, right? So with this I think we go for a quick break and come back to the topic again.
हेलो एवरीवन, आई एम डॉक्टर सचिन कुमार और मैं आ रहा हूं एस चांद एकेडमी पे बीएससी फिजिक्स के बहुत सारे टॉपिक्स लेकर सिर्फ आपके लिए। बेल आइकन ज़रूर प्रेस कीजिए सब्सक्रिप्शन के साथ, ताकि हम जुड़े रहें और आपको ऐसे टॉपिक्स कराते रहें।
Welcome back to the lecture on S. Chand Academy. If you have any doubts, you can refer to our previous lectures also. And getting back over to the topic, as I was just telling you that benzene can undergo electrophilic substitution reactions in the presence of Lewis acids. So these Lewis acids are required so that the electrophilicity of the attacking electrophile may be increased. So why we want that? We want that because benzene is going to lose its aromatic structure. So in order to lose its aromatic structure, we need to have an electrophile which is as much active as possible. So in this case, for example, I am giving you a set of reactions over here to go through, and all of these reactions, say if we start with the chlorination, which is an important example of halogenation reaction, the Lewis acid used over in the chlorination reaction is aluminium trichloride. For bromination, we use FeBr3. For nitration, the Lewis acid we use is sulfuric acids. In almost all the electrophilic substitution reaction, there is a requirement of a Lewis acid. The thing will become much more clear if we go to the individual reaction. So before we go to the individual reaction, let's look at the general mechanism of electrophilic aromatic substitution reaction. Suppose we have benzene and it attacks an electrophile, so it will lose the aromaticity at once it will react with the electrophile. So here comes a positive charge, and this positive charge can be stabilized by the other pi electrons in the ring. So this intermediate is resonance stabilized. In this intermediate, a pi bond is broken and a sigma bond is formed. You can see that one of the carbon is now on which the electrophile is attached is not sp2, it is sp3 hybridized, and this positive charge is being shared by other 5 carbon atoms. Okay, and this can be represented by a resonance hybrid where there is a partial positive charge on 5 carbon atoms, and this intermediate is also known as erinium ion. इसको हम erinium ion कहते हैं. Why I am saying partial positive? Because the 6th carbon is not having the positive charge. Also, this is not aromatic because इसमें कितने pi electrons हैं? 4. And benzene, why it is aromatic? Because it has 6 pi electrons. So 4n plus 2 benzene में क्या हो जाता है आपका? 6. So n is equal to 1. But here pi electrons are not even in conjugation. So rhenium ion is not aromatic. So activation energy जो हमारी है electrophilic aromatic substitutions के केस में it's quite high for the first step. The first step, which is for the formation of the erinium ion. For the formation of erinium ion, the activation energy is quite high as compared to the second step, which is the loss of a H plus ion to form the substituted benzene ring. So because of this high activation energy, we need to use Lewis acids in electrophilic substitution. Coming back to the mechanism which I was just discussing. So once the erinium ion is formed, it will again lose a proton to the conjugate base which we have got from the Lewis acid, and the product will be a mono-substituted benzene. Please see carefully that in this compound, one of the hydrogen atom of the benzene has been replaced by an electrophile. So electrophile which we wanted has been placed suitably on the benzene ring, right? And this is the most simple and the general mechanism for electrophilic substitution reaction. So this mechanism has explained us the basic thing, that how the electrophile attacks, what is the resonance stabilized structure, and why do we need the Lewis acid in the case of electrophilic aromatic substitution reactions. Looking at the first reaction in this category, which is the halogenation reaction. Now halogenation of the benzene ring can be by using the halogens obviously. So we have fluorine, chlorine, bromine and iodine, and the order of the reactivity of these halogen is as follows. Fluorine being highly reactive is not of much use. Iodine being too less reactive is also not much of use. Iodine although can be used, but there are special conditions for introducing iodo group onto the benzene ring. So the two basic reagents which we use for the halogenation of the benzene ring are chlorine and bromine. And for chlorine, as I just said, we have to use aluminium trichloride as a catalyst because AlCl3 increases the electrophilicity of the chlorine atom on the chlorine, and therefore it can easily be attacked by the benzene ring and can give you the suitable rhenium ion, which can further lose an H plus ion to give you the corresponding mono substituted benzene or the chloro substituted benzene. And similarly will be the case for the bromination. For bromination we will use Lewis acid as FeBr3. Let's move to the next important electrophilic aromatic substitution reaction, which is nitration reaction. Nitration is another important reaction where the electrophile is nitronium ion. What is the electrophile in the nitration reaction? Nitronium ion. Nitronium ion कैसे बनता है? The nitronium ion is formed when H2SO4, the Lewis acid in this reaction, reacts with nitric acid. So both of these reagents have to be fuming. We usually try to take fuming nitric acid and concentrated sulfuric acid for this reaction so that there are no traces of water, because water, if there in this reaction, it will retard the rate of the reaction. So once the nitronium ion is formed, it will be attacked by the benzene ring. Addition of the electrophile onto the benzene ring takes place, and with the loss of the H plus ion at the later stages will give the corresponding nitrobenzene. Other than the nitric acid and sulfuric acid, there are other reagents also which can be used for nitration. Say for example, nitronium tetrafluoroborate, nitronium hexafluorophosphate, ethanol nitrate. So these are the alternative nitrating agents which one can use for nitration reactions. Let's come to the sulfonation reaction. Sulfonation can take place in the presence of fuming sulfuric acid. Now how we get fuming sulfuric acid? Fuming sulfuric acid is the common name for a solution of 7% sulfur trioxide in sulfuric acid. So sulfur trioxide क्या है? Sulfur trioxide is anhydride of sulfuric acid. So this sulfur trioxide is the actual and the strong electrophile in the sulfonation of benzene ring. So from the sulfur trioxide and sulfuric acid we get the required electrophile and it attacks the benzene ring and we get the sulfonic acid, the corresponding benzene sulfonic acid. And these are of commercial importance because they are used to synthesize detergents also, like alkyl benzene sulfonates are important components of soap industry, the detergent industry. They are used in the detergents also. And the desulfonation of benzene I initially mentioned while the preparation of aromatic hydrocarbons also, that the desulfonation gives back the benzene ring. So sulfonation is a reversible reaction. So one has to keep this point in mind while synthesizing sulfonated substituted benzene ring. The next reaction of the benzene is alkylation using the alkyl halide. This also takes place in the presence of a Lewis acid to give the corresponding alkyl substituted benzene. Important thing to remember in this reaction is that whenever we use any alkyl halide, say for example we are using say for example this is the alkyl group which we are using, then this will undergo rearrangement. Any alkyl group can undergo rearrangement to give a stable carbocation, and then that corresponding intermediate will be preferred to be attacked by the benzene. So carbocation rearrangement, carbocation is the electrophile in this reaction, and carbocation is capable of undergoing, the more stable the carbocation will be formed and that will be attacked by the benzene ring during the formation of alkyl substituted benzenes. So the important is the major disadvantage of this reaction is that the straight chain alkyl substitution is difficult to obtain. So whatever branched alkyl halide we are taking, it will tend to undergo rearrangement to give more stable carbocation. And the last set of the reaction which aromatic hydrocarbons undergo is Friedel-Craft acylation reaction. This we have already encountered at many places in our previous videos also. Friedel-Craft acylation, as the name suggests, is the introduction of acyl group into the benzene ring, and the precursor for this is acyl chloride, again in the presence of Lewis acid AlCl3. So the electrophile will be acylium ion. This is acylium ion. So acylium ion will be the electrophile. It will be attacked by the benzene ring, and the product will be corresponding acyl substituted benzene. These acyl substituted benzene can be reduced by the catalytic hydrogenation method to give alkyl substituted benzene. So this method is better as compared to Friedel-Craft alkylation method to synthesize alkyl substituted benzene. With this we come to an end of this discussion. I hope you liked our video. For more such videos you can log into our channel by S. Chand Academy, and for more information please refer to our books by S. Chand Publishing, the link to which is given in the description box below. Hope you enjoyed today's discussion. Thank you and have a good day.